The first part of the notes here is just talking about some prerequisite information you need to know. We've kind of already talked about this stuff. If you're having any trouble with that factoring assignment that I gave you, please do what you need to do to get comfortable with that. You're going to be doing a lot of factoring. We will not be covering factoring in this class. If it comes up, I'm going to do it. I'm not going to stop and explain how to do it. Okay. But feel free to see me or do a good old YouTube search. It's usually pretty easy to find some good information on that. So we are talking about functions. Just to give you a broad outline of this semester, Chapter 1 is all about analyzing functions. In Chapter 1, we're going to learn the tools to look at a function, figure out what its graph looks like, look at its graph, and talk about lots and lots of different properties of that function. And these properties are going to end up becoming really important for what we're going to do in chapters 2 and 3. Chapter 2 and 3, we're going to kind of expand that and look at some specific types of functions, but we'll still be doing all of this stuff from chapter 1. So domain and range, increasing, decreasing, local maxes and mins, all that kind of stuff. So chapter 1 is all about building that tool set, and then chapter 2 and 3 are using that to analyze special types of functions. Chapter 2 is all polynomials and rationals. Chapter 3, we get into logs and exponentials and logistic functions. So super, super important that the stuff that we're learning here in chapter 1, that you guys are really, truly learning it, because you're going to use it every single chapter for the rest of the year, even second semester when we get into trig functions. So let's get into it. First of all, I want to make sure we're comfortable with the definition of a function is. Function is a rule that pairs each input with at most one output. In other words, a function cannot have, or an input cannot have more than one output. So we're going to use that to analyze whether these 4 equations represent functions of x. So is this first one a function? If you were to look at y equals 2x, is that a function? I would say yes, it is. And the reason is that each input, when we say input, we're typically talking about x values. Each input has how many outputs? Has one output. We're typically talking about y's. And as we're doing these, I've picked examples that are similar to what you're going to see in your assignment. Now, in your assignment, you don't need to keep writing this out every time it's yes. You can just say yes. If it's no, I want some explanation though. Second one, function or no? No? Can you give me an example of an x value of an input that would result in 2 or more different outputs? Yeah. So if x equals 2, then what would y equal? Y would equal 2 plus or minus 1, which means y is equal to 2 plus 1, which is 3, or 2 minus 1, which is 1. So we've come up with an example of an input that's giving us 2 different outputs, which means no, it is not a function. I have a question for you. Is every input going to have 2 outputs for this particular rule? Can you give me an example of an input that would result in only 1 output? Or 0 outputs? Or 3? So let me pose the question again. Is every input going to have 2 outputs for this one? I'd say yeah. Because no matter what, we're going to add 1 and subtract 1. We're going to get 2 different numbers for it, right? Whether we do decimals or fractions or negatives or positive. So no, because each input has 2 outputs. See if I can spell right here. Squeeze that E in there. You guys are going to get used to my terrible handwriting over time, but until that happens, please feel free to ask for me to translate. That is the worst W I've drawn today. So when you run into a problem like this on the assignment, it's going to ask you, is it a function? If not, explain why. You're going to explain why by saying something like this or by giving an example. Okay. All right. Now our next one looks a little bit weird because it's x equals 3y, but the question is the same. Is y a function of x? So if you run into an equation that's an x equals instead of y equals, my recommendation is go ahead and solve it for y. And that sometimes makes it a little bit clearer whether it's going to be a function or not. So if I were going to solve this for y, I would divide on both sides by 3, and I get x over 3 equals y, or y equals 1/3 x would be another way I could write that. So I'm going to make myself a note here to solve for y. So is this a function? Does every input have only one output? Yeah, it would. So we would just say yes for the same reason up above. I'm not going to copy down that whole each input has one output thing. We've done that once. This last one's also an x equals. Could you all take a minute for me and get y by itself in that equation? Solve that for y. Do a couple steps of algebra here. What do I do first? I'd probably subtract 1 from both sides. And then take a square root on both sides. And I have forgotten something really important. What did I forget? Plus or minus. When we take a square root on both sides while we're solving an equation, we got to take into account plus or minus. When you're solving and you're taking a square root on both sides, yeah, you have to take into account plus or minus. So y equals plus or minus the square root of x minus 1. What's our gut instinct? Function or no? No. Can somebody come up with an example before we commit to this? Can somebody come up with an example? If the answer is no, then there must be some input that's giving me more than one output. Can you come up with an x value I could plug in here that would give me more than one y value? Yeah. Let's try 5. So if x equals 5, then y would equal plus or minus the square root of 5 minus 1. That's plus or minus the square root of 4, which is 2 or negative 2. So we came up with 2 outputs for that particular input. So my answer is no, it's not a function. Can we give the same reason we did up above? Is every input going to give us 2 outputs for this one? I have a challenge for you. Can you come up with an input that is only going to give you 1 output for this one? Think about that for a second. I'm not calling you a second, but don't say it yet. Can you come up with an input that would only give you 1 output? Allie, what are you coming up with? Yeah. If x is 1, right, then we'd be doing plus or minus the square root of 0, which would be 0 and 0, right, which is the same thing. There's only 1 output there. All right, all right. I'm impressed. Could you come up with an input that would give me no outputs? Zero. Right. So when we're talking about functions in this chapter, we're going to be talking about functions in the real numbers only. So I would say 0 would give us no outputs, no real outputs anyways. So yeah, or anything less than 0 would work also, right? Actually, anything less than 1 would work. So if I plug 0 in here, I'd be taking plus or minus the square root of negative 1. That's not going to give us a real number, so it would have no output. So I would say for my explanation here, I would say each input, or I'm sorry, not each input, some inputs have two outputs. And some inputs only have one, and some inputs have zero. And it's okay to have only one, and it's okay to have zero, but you cannot have any inputs that would have two outputs. Okay. Which, if that happens, if you can find a single example like this where you're putting in a single input, getting two outputs, then game's over, not a function. All right, could you guys show me on your thumb meter how you're feeling? If I give you an equation, x's and y's, could you tell me whether it's a function or not, and maybe come up with an example if it's not? We feeling pretty confident with that? All right, you guys are doing great. Vertical line test, I don't want to spend too long on this because my expectation is you've seen this at least 3 or 4 times in your math career. Yes? Vertical line test. Why don't you do this for me? Could you draw me a couple XY axes here underneath? And show me what you know. Could you draw me 2 different graphs? I would like one of your graphs to pass the vertical line test, and I would like one of your graphs to fail the vertical line test. Show me what you know here. Something that passes and something that fails. I'm going to draw a couple here. I like parabolas. I'm feeling parabolas today. I saw several parabolas as I was walking around there. Here's a parabola that opens upwards. Does that pass the vertical line test? It does, because I can draw any vertical line that I want on this graph, and it will only ever touch my graph in one spot. That means it passes the vertical line test. Here's a sideways opening parabola. Does that pass the vertical line test? It does not, because there are many places that I can draw a vertical line where it touches the graph in more than one place. So if it passes the vertical line test, what's that mean? That means it's a function. That means it's a function. So this is a function, but this one is not. So I need you to be able to look at a graph and be able to just quickly sweep a pencil across it and say, yes, it's a function, or no, it's not. Once or at most one time. Right, so let me show you an example of a function. Anybody know what function I'm attempting to draw there? Square root function, that would be the parent function. This particular function, I could draw a vertical line here and it's not touching anywhere. Is that a problem? No, no, it's not allowed to touch more than once. It can touch once or it can touch 0 times, but it can't touch more than once. And it's really just a graphical interpretation of this rule up here, isn't it? Yeah. So yeah, because the x value is the input. So we have picked an input here. We picked an x value, and we drew a vertical line there. And we're showing that that particular input's going to give us 2 points or two y values, 2 outputs. All right. We're going to start talking about domain and range now. And this is going to be really the key part of our lesson today. Are you guys comfortable with domain goes with X and range goes with Y? You've been seeing this for a while, right? Domain are the inputs, range are the outputs. Domain is really what it is. It's a collection of all the possible input values, all of the numbers that you can put in to X and get a valid output from that function. Range is the set of all the outputs you're going to get out of it. We're going to get into range later on. We won't mess with that too much today. Our main goal for today is, if I give you a function, can you find the domain of that function algebraically? Folks, when I say algebraically, that means I want to see some work. So you're going to see some problems in your assignment that are going to ask you to find the domain algebraically. That means I want to see some steps for this, and I'm going to model for you today kind of the minimum steps that I want to see in your assignment. I will be picky about your assignments. Okay, when I check your work on Friday, if you're not showing me enough steps, you might get a 3 out of 4. Okay, I've got some support for you, and I'll talk more about that when we talk about our assignment. You'll know exactly what I want to see for this first assignment. Okay, we'll talk more about that later. Okay. So when we're talking about domain algebraically, what we're going to focus on are things that could cause problems for us in a function. There are certain rules in math that you guys have learned over the years, especially rules that deal with like fractions and radicals. What's the big rule for fractions? What's like not allowed when you're dealing with fractions? 0. You can't have 0 where? Numerator or denominator? Denominator. You cannot have a 0 in the denominator. You cannot divide by 0. Okay, it doesn't make sense. It's not mathematically defined. If it was possible and you succeeded, the universe would implode on itself and bad things would happen. So we cannot divide by 0. What about radicals? If we're trying to not deal with any complex or imaginary numbers, what's the rule about the inside of radicals? You can't have negatives in there, right? We got to avoid negatives in there. Now, when we're talking about domain, we're talking about things that we are allowed to put in there, not things that we're not allowed to put in there. So we kind of got to flip our viewpoint a little bit and think not about what are we not allowed to have, but what must we have in order for it to work. Okay, so if I've got a fraction, what must be true about that, the bottom of that fraction, in order for me to be able to deal with it? The bottom of the fraction must be what? Greater than 0 or less than 0, right? I'm going to say the main restriction for a fraction is that the denominator must be not equal to 0. Right? Domain is what we're allowed to put in. We're allowed to put in anything that causes the denominator to not be equal to 0. This is our restriction. And this is going to be the absolute key thing as we deal with finding domain algebraically. So we're going to go through some examples here, and I'll kind of take you through my thought process. So I look at this first function here, and I'm going to start looking for problem areas. Problem areas would be anything that's in the bottom of a fraction or anything that's inside of a radical. So in this case, this x plus 5, that's not a problem area to me. I have no concerns about x plus 5. What I do have some concerns about are x minus 1. We can't let that equal to 0. So this is what's going to immediately grab my eye, this x minus 1 here. That could potentially cause us some issues. So what we're going to do is we're going to copy that expression, that x minus 1, just that portion of the function, and we're going to apply the restriction to it. The restriction is that that denominator must be not equal to 0. This step right here is the key step of doing these problems. And when we eventually take a test over this, that step will be worth points. You may not skip that step, okay? This, by showing me this, by writing this on your page, I have evidence that you know that this could potentially cause problems, but it's gonna be okay as long as we make sure that it's not equal to 0. That's what we're saying here. You guys following me so far? So we're going to take this equation that results, this restriction, we're going to solve it, we're going to graph it, and then we're going to put it into interval notation, and that'll be our domain. Okay? So from here on out, this is all stuff that you've seen a lot of times. So let's solve this thing. Remember, I told you, you do not have to show me +1 on both sides anymore if you don't want to. I will not be showing that in the notes. If I did +1 on both sides, I would get x not equal to 1. That would be my result. And that's solved. The x is by itself. Let's go ahead and graph this on a number line. My number lines in this class, I like you to have 0 always on your number line, and then just any other important points. You don't have to draw 1,000 tick marks. Just the important points. 1 is my important point there. And when I go to graph this, what kind of dot do I want to have at 1? Open, closed, open, because 1 is not included, agreed? X cannot be 1, so we'll have an open dot there. Arrows to the left, to the right, both? Both. What we're showing here is that X can be anything on the number line as long as it's not that 1 there. I mentioned this last week. In this first chapter, I'm going to insist that anytime we're talking about domain and range or anything else involving intervals, we're going to use interval notation. Okay. The reason for that is I just want you guys to be super comfortable with interval notation. So let's go ahead and write this out. This is our domain. Our domain for this particular function starts at -infinity, goes right up to 1, does not include 1. We pick up on the other side of 1 and we go up to +infinity. So that would be my final answer. And if I'm looking at your assignment next Friday, or if I ask you to find a domain for a problem like this on a test, I want to see all of those steps. Okay. I want to see and this is key. This is the big one here. Just so you know, when we get to chapter 2, I'm going to ease up a little bit and you'll be writing this instead, all real numbers except 1 later. Okay. I will let you do that when we get to chapter 2, but for chapter 1, I must insist that we just practice with that interval notation. The reason is we're going to get into some pretty messy interval notation later on in the context of some pretty complicated stuff. I don't want you guys to have to think about the interval notation. I want to get to the point where it's like muscle memory. Okay. And I found that if I can get you to just give me all interval notation answers in chapter 1, we'll get you there. You guys have any questions back there? I'm worried that you might be disrupting people around you. Could you guys pause on the conversations? And if you do have any questions, just let me know. I'd be happy to address them. Okay, any questions on A before we move on? Okay, let's talk through B. So my thought process is I'm gonna look at this and I'm look for problem areas. So this X up top, no issues. However, there's an X plus 1 in the denominator that could cause some problems. Oh, I got another denominator here too. X squared minus 4 could also potentially give me some issues. So we're going to have to deal with both of those in this one. So let's go ahead and do our key step here. Our key step is to write both of those things with the restrictions on it. So X plus 1 and X squared minus 4. And what must be true about both of those? They must not equal 0. So X plus 1 not equal to 0 and X squared minus 4 not equal to 0. I've got to see this step. Okay, make sure you're showing me this step. Put a little star next to both of these. All right, solve them. Solve them. Show me your algebra skills. So I'm coming up with 3 different problem values for X this time. Are you getting 3? Did you remember to do the plus or minus when you took that square root? Did anybody solve this second one by factoring and using zero product property instead? That would have been a possibility. We're going to see that come up later. All right, so are we good with x can't be -1 or -2 or +2? We good? Yes. All right, and in chapter 2, you'll just write all real numbers except for -1, -2, and +2. But here, I'm going to be a big meanie pants and make you draw a number line and graph it and give it to me in an interval notation. So important values here: -1, -2, and +2. We'll have open dots at each of those and then fill in the rest of our number line. And our interval notation is going to get kind of messy in this one. We have dealt with worse. Yes, we have. It's our domain. All right. So I want to pause and just kind of look at big picture stuff here. What is it that we're trying to accomplish? It's sometimes you're going to find that we're going to get into the weeds a lot on the detail stuff in this class. But like I told you last Wednesday, we're moving from kind of cookie cutter math into more analytic math. So what we're doing here is a process, but it's really important we understand what we're actually doing, because I'm not just going to give you a test where I ask you to do this a bunch of times. I'm going to give you a test. You'll do this a couple of times, but then you're going to have some really broad problems where this is just going to be one thing, one of your tools you're going to pull out to help solve that. So it's one thing to know how to do it, but you need to understand what you're actually doing here. So what are we doing? What is the purpose of all this? Right here, what are we ultimately doing? What are we trying to do? Yeah, we're finding what x is allowed to be. We're finding the domain, which is all the x's that are allowed to go into these functions. If I gave you a problem, let's say I gave you this domain right here, and I said, what could I ask you about this? How about this? If I just gave you this domain right here, I could ask you on a test, would the graph of this function have a y-intercept, yes or no? And you would need to be able to answer that question. I'm talking about this second one here. Would the graph of this function have a y-intercept, yes or no? Answer is yes. Could you explain to me why it would have to have a y-intercept? I want to give everybody a chance to think about it really quick. Can you give me, I don't want a full answer, can you give me a key connection? X equals 0 is kind of the key. That's a great hint, right? Because what happens on a function when x is equal to 0? That is your y-intercept, right? If the function, if there is a point on the function where x is equal to 0, that is your y-intercept. It's got to be, right? Can you look at this interval notation and see that 0 is part of this? Yes. That means that 0 is in the domain. That means there is a point on this graph that has an x coordinate of 0, and that point would have to be on the y-axis. So this does absolutely have a y-intercept. What about this one up here? Does this have a y-intercept? It does. Yeah. So that's the kind of thing, that's the type of question you're going to see on your tests and quizzes. So as you're working through your assignments, it's important that you're understanding all the steps that you're doing, but you also need to take a moment every now and then and be like, okay, why am I doing this? What's the purpose of all this? What are some potential ways we could use this in the future? So All right, let's keep going. You guys are doing awesome. All right, radicals. So these are specifically radicals with even roots. You guys told me a minute ago that we were not allowed to have what inside of radicals, inside of square roots? We're not allowed to have negative numbers. Let's flip that on its head. We're not allowed to have negative numbers, so that means what must be true about the inside of a radical? Positive or equal to 0. We can take the square root of 0, can't we? Yep, so I would say the inside of a radical must be greater than or equal to 0. It cannot be negative, which means it must be greater than or equal to 0. So we're going to tackle these problems very similarly to what we just did. We're going to look for those problem areas, and we're going to apply this restriction. It's a different restriction this time. So let's look at part A together. And I start looking through this. Now, am I worried about this 5 on the outside? No, it's not in a fraction. It's not inside of a square root, so we don't have to worry about that. -3, same idea. The problem area that I see for this particular function is that 1 minus 2x. It's underneath the square root there. That could cause us problems if we don't put the right stuff in there. So let's do our key step here. Let's write down 1 minus 2x. I'm not writing down the radical, just the part that's inside of it. And let's apply this restriction. The restriction is that if it's inside of a square root, it must be greater than or equal to 0. All right, let's take a moment, do a few steps of algebra and solve that. You may find yourself dividing on both sides of by a negative number when you're solving this. Do you remember what you have to do with inequalities when that happens? You got to flip the sign. If you end up dividing or multiplying on both sides by a negative number, you have to flip the inequality. Okay, so keep an eye out for that. So I'm actually going to show my steps this time because I want to illustrate that as a reminder. -1 on both sides gets me -2x greater than or equal to -1. And then to get x by itself, I would divide on both sides by a negative. Oh, there we go. Dividing on both sides by a negative, I must flip the sign so that greater than or equal to becomes a less than or equal to. And that would be 1/2. Okay, big picture, what does that mean? That means as long as x is less than or equal to 1/2, then what? Function's going to work. We're going to be just fine. Let's go ahead and graph this to make it a little bit easier to put into interval notation, and then we'll be done with this one. At 1/2, am I looking at an open dot or closed dot? Closed dot because of the or equal to part, right? And we're graphing where x is. It says x is less than, so we need to draw an arrow in the less than direction. And that'll get us our domain. Could I get you all to please practice right now and also on your assignments, making sure that it's very clear whether you're giving me a square bracket or a parenthesis, okay? When we get to our first test, I don't want to have to guess. If I got to guess, I can't give you full credit, okay? Make it very clear to me, please. All right, so this is kind of similar to what we were just doing, right? The big difference is the restriction. Instead of writing not equal to 0, we wrote greater than or equal to 0. Other than that, it's pretty much the same idea, right? Look for the problem area, apply the restriction, solve it, graph it. That's your domain. Any questions on A? Before we move on to B, B is tricky. Guys, I need your full attention on this one, okay? We're gonna kind of get in the weeds a little bit on this one. You're gonna have questions. Any questions before we start? Fourth roots. Now, before we get into this, you guys are comfortable, right, with the fact that cube roots don't have restrictions. Are we okay with that? You can take the cube root of a negative number. You're going to get a negative answer. Okay, it's not imaginary. Same thing with fifth roots and seventh roots. So odd roots, you don't got to worry about odd numbered roots. There's no restrictions on those. We do have to worry about any even numbered roots. So the fact that this is a fourth root tells me that I do have to worry about this stuff on the inside. So let's take the potentially problematic stuff on the inside, that x squared minus 25, and let's apply our restriction to it. It was inside of an even root, so it must be greater than or equal to 0. All right, here's the tricky part of this one. We need to solve that. Do you guys know how to solve quadratic inequalities algebraically? I'm going to guess the answer is no. Last class, nobody really knew how to do it. Do you remember making sign charts last year to solve inequalities? Probably in your polynomials unit. No, I may not have been covered in the Algebra 2 curriculum. I'm pretty sure my students haven't been familiar with it. Now we're going to go over that in chapter 2, but right now you probably do not have the skill that you need to solve this inequality. I will tell you right now that you cannot just add 25 to both sides and take a square root on both sides with a plus or minus. That does not work for inequalities. That works for equations, but it does not work for inequalities. Okay. You could factor that thing with the difference of squares and get a new inequality, but zero product property, you can't split those two factors up either. That works for equations, but not for inequalities. You had a question a second ago. What do you? It looks like I'm going to show you this, but I don't want you to worry about trying to copy this down because we will spend like a whole class period going over this. It looks like this. Okay, I'm going to show you this. It's not a big deal. It's not a huge thing. Okay. And we'll get there and you don't even have to worry about it right now. Because here's why. Okay. And this is going back to something we did on Friday. I expect you all to be able to solve this equation by some other means. Now we're not going to solve this algebraically. We're actually going to solve this graphically. So we kind of went over an example. Do you remember on Friday when we went over an example of looking at an equation that said y equals, I think it was x squared minus 4. Do you remember that? And I told you, you are going to need to be able to look at x squared minus 4 or x squared minus 25, and you're going to need to know what that graph looks like. You should be able to make a sketch of this graph. Pretty accurate sketch with x and y intercepts. In fact, could you go ahead and do that for me right now? Just take this x squared minus 25, and let's go ahead and write over here y equals x squared minus 25. Make me a nice graph of what that, or sketch of what that graph would look like. Label your any intercepts that you have there. We should be able to do this fairly quickly and accurately. You guys are great. Look at you go. See parabolas. I'm seeing some parabolas. Parabolas are opening. Which direction are parabolas opening? Opening upwards. Excellent. I can tell because of the negative 25, it's going to have a y-intercept at negative 25, right? We could factor this. That's going to help us find our x-intercepts. Where are our x-intercepts going to be? Negative 5 and positive 5. And we know it's going to be opening upwards, okay? So we're envisioning this in our head and we're sketching it on our paper. If you have a question about what we just did there, please ask. We're going to go on to talk about how we're going to use that to solve this equation. You guys good? All right, eyes up here, don't miss this. We're gonna make a pretty big leap here, and this is where my students tend to have trouble on this particular example. Remember what we're trying to do, okay? We're trying to solve this inequality. We're trying to find all the x values that make this thing true. This says x squared minus 25 is greater than or equal to 0. Now, when I'm graphing this and I'm thinking greater than or equal to 0, am I thinking about the top part of this graph or the bottom part of this graph or right along the x-axis or some combination of those? X-axis and up. Can you please highlight this graph, all of the points on this graph where this graph is greater than or equal to 0? Highlight them. You can just make it darker with your pencil. I'm going to use a different color, but I would say we're talking about this part of the graph right here and this part of the graph right here. That is where this graph is greater than or equal to 0. Agreed? All right, well, what are those x values that I just highlighted? Negative infinity to negative 5, 5 to infinity. So that's going to be my domain. Let me write this down, and then we're gonna back it up, and we're gonna pause and look at a big picture here. So if it had said less than or equal to 0, we'd be looking at that U-shaped piece underneath, right? There's a lot of moving parts going on, and there's several layers of kind of big picture, smaller picture. So I want to make sure that we're feeling good about this. All right, so big picture, what are we trying to do? We're trying to find a domain. We're trying to find all the x values that are allowed to go into this function without causing problems, right? So how do we do that? Well, we identified the problem area. It was the portion underneath that radical, that x squared minus 25. And we said the restriction on this, in order to make everything run smoothly, we got to make sure that x squared minus 25 is greater than or equal to 0. Whatever's under the radicals got to be greater than or equal to 0. That's how we got this. And again, this is kind of the key step. So that's kind of the kind of big idea, maybe new, I'm not sure. But that's the big idea for today. Now, after that, it's just kind of details. We're just trying to solve this. We don't have the tools to solve this algebraically. We've got to start asking ourselves questions. Well, what else could I use to solve it? We've dealt with when are things greater than or equal to 0. That's why we practiced all that stuff last week, right? We know what the graph of this thing is going to look like. So we're like, well, let's try and solve it graphically. So we graphed this thing, and we did it by hand. Now, if you were completely unsure what this graph was going to look like, you should have a graphing calculator that you could use to get you unstuck with that, right? We graphed this by hand, and greater than or equal to 0, we know what that is. It's the part that's up above the x-axis. So we highlight that part. We look at those values, stick it into some interval notation, and that gets us there. How did we know to do this? That's the big question. And how are you going to know to do this? It's an option. It's one of the tools that we have in our tool chest. If we don't have an algebraic way of doing this, we got to start asking questions. Well, how else could I potentially solve this thing? And solving something graphically is something that we will be doing fairly regularly in this class. So, all right, this is kind of a messy one. You guys feeling all right about that? Now, so I'm going to tell you in chapter 1 for now. Those are the only two restrictions that we're going to need to worry about. Rational functions, the denominator must be greater than, or must be not equal to 0. Even radicals, the inside must be greater than or equal to 0. We are going to add on to this as we go forward. So when we get into chapter 3 and we start talking about logs, there are some other restrictions for logs. Does anybody remember what you're allowed to put inside a log? So logs are only positive numbers. So when we run into problems with logs, our restriction is going to be greater than 0, not greater than or equal to, strictly greater than 0, because you can't take the log of 0. When we get into second semester, we'll get into inverse sine and inverse cosine. Those have some other restrictions on them. You can't put any number into an inverse sine or an inverse cosine outside of -1 to +1. So those are you can only put numbers between -1 and +1 inclusive into those two things. So we're going to expand on this, but we'll be using the same technique. So I want you to get comfortable with this technique. And again, this part where I put that star next to it, that step there, that's the key piece. If you can kind of get yourself to the point where you're like, okay, I'm looking at this function. Where are my problem areas? Let me write this down. What's the restriction on that to make sure this function is going to work smoothly? Anybody have any questions right now over this page before we go into our last example? You guys are doing really well. I love the questions you're asking. We got, how are we doing for time? We're doing great. Yes. Yeah, you don't have to ask. The pass is back there. Folks, if the pass is in the back of the room, just grab it and go. If the pass is not there and you're like, I got to go right now, or there's going to be a mess, then get my attention and just say, hey, I'm leaving. Okay. Back one. Oh, I love this problem. So this is great. I'm going to tell you right now that this will probably be the most challenging domain problem that you're going to see in this chapter. Okay. You will not see anything like this on your assignments. I don't think so. Definitely not on your tests. So this one's gonna force us to pull a whole bunch of information that we've just been talking about together, but you guys got this. Okay. So let's look through this thing and see where our problem areas are. Right now, we know that we're going to be focusing on fractions and even roots. Let's start with fractions. Do you see a fraction? Yes. Does the denominator of that fraction have any x's in it? Yes. I'm going to draw a box around this entire denominator because that is the denominator. We have to deal, when we're dealing with denominators, we got to deal with the whole denominator. Let's write it down here. Potential problem area. And let's apply our restriction to it. That came from the denominator of a fraction. Our restriction is it must be not equal to 0. We'll come back and solve that in a moment. Before we go doing that, why don't we look and see if there are any other issues that we might encounter here? Do you see any radicals? Tell me, do we need to worry about this 5 plus x here? No, because odd root. You guys are awesome. What about the 2 minus x? Could cause us problems because it is inside of a radical, an even radical. So let's write that potential problem down. That 2 minus x is the thing we got to keep an eye on. It's going to be all good as long as, what's our restriction here? Greater than or equal to 0. You guys are great. But wait, I do see one other potential area of issue. There is an x plus 3 also inside of a radical here. We have to deal with that. It doesn't matter that it's already over here. We've got to deal with the fact that that is a radical. So we're going to think of it as it's kind of its own potential problem. We'll write down that x plus 3, and we'll apply the restriction to that as well. It's in a radical, so it must be greater than or equal to 0. Okay, so sometimes you're going to have some of these problem areas that are actually inside of other ones. I need you to know that when you're dealing with rational functions, that's a fraction, the entire fraction is not equal to 0. The entire bottom of the fraction is not equal to 0. And with the roots, the entire inside of the root is greater than or equal to 0. Any questions up to here? This is the key step. If I put a problem like this on the test and you wrote out this much of it correctly, you got half of the points for this. Okay, I need to see this step. Make sure you're writing this down in your notes. Okay, from here we're going to solve. When you're looking at this one, this is like an equation, even though it's a not equals. I'm not sure if you guys are seeing this yet. When you look at this, are you noticing that there are 2 factors here being multiplied equal to 0? Anybody notice that? That's that 0 product property thing that you used a lot last year, especially with quadratics and polynomials. What are we allowed to do with those 2 factors if they're being multiplied equal to 0? We can split them up and we can set them each equal to 0. That's how I'm going to solve this thing. So I'm going to make 2 equations out of this. X minus 1 equals 0, not equal to 0. And the square root of x plus 3 not equal to 0. We're just solving this by splitting it up into those 2 factors. And then we'll just do our algebra steps on those and solve them. We're going to get x not equal to 1. This one, let's solve this one here. Well, I got to get rid of this radical. Let's square both sides. Zero squared is just still 0 though, right? And then we'll get rid of that 3. So minus 3 on both sides gets us x not equal to -3. No, not for this. Let me come back to that in a minute, okay? I want to focus on this for right now, but can you jot that down in your margin, put a star next to it so I don't forget, please? The question was, do we need to do a plus or minus here? We do the plus or minus when we're taking a square root on both sides, not when we're squaring both sides. And we'll talk about why that is in just a minute. All right, so this is what I would call, this is a part of a subdomain, and we're going to graph this for a second, but let's go ahead and solve these other two, find our other two subdomains too. So go ahead and get x by itself in those other two. We might end up flipping our inequality here because we're going to have to get rid of that negative either by multiplying or dividing on both sides by a -1. Ooh, what did I screw up there? I didn't flip it, did I? Wow. Just was talking about that too. So that's one of our subdomains, and then this one here, -3 on both sides. Oh, that's easy. Easy street. So we're dealing with 3 separate restrictions here. Which of those 3 restrictions have to be true in order for this function to work? All of them do. So we need to come up with a domain that kind of links all 3 of these things together. This gets a little bit tricky, but this is where doing a number line is going to make things a lot easier for us. So what I'm going to do is I'm going to make a number line. I'm going to leave a lot of space above it because I'm going to actually make 3 separate graphs above that number line. And we're going to see where all of those graphs intersect each other, where they overlap. So draw your number line, leave a little space above it. And let's get all our important values. So anything that appeared in any of these 3 are going to be important values. So the smallest one is -3. We've also got 1 and 2 in there. I've color coded mine, but you can just kind of draw yourself a little arrow. So let's do this first one right above the number line, and then we'll stack the other 2 sort of on top of that. So our first restriction came from the denominator not equal to 0. We ended up getting x can't be 1 or -3. So let's do some open dots at 1 and -3 and fill in the rest of the number line. That's not the domain for the whole function. That's just the domain for just this portion of it on the bottom, right? I'm going to do the second one right above it. Less than or equal to 2. So at 2, I'm going to have a closed dot. And then less than is going to move off to the left from there. And then my last one, I'll stack right on top of that one. Greater than or equal to -3. So again, closed dot at -3. Greater than means we need to go to the right. Our final answer, our final domain is going to be all of the values where all 3 of those things are true. So we need to find any regions or points on this graph where it's overlapped by all three of those. And I like to go through region by region, point by point. I usually start at the left-hand side. I'm going to do my final one down below. So this is going to be my final domain. So look at this region over here. Are we seeing all three of them there? So that's not in my final domain. What about at -3? Are they all there? Nope. Because of the open dot right there, right? What about between -3 and 0? Yes. So that is going to be part of my final domain because all three of the graphs overlap in that region. But we said it did not overlap at -3, so we're going to want an open dot there. Actually, this shouldn't stop at 0. Where should it go? Should go all the way to 1. Should it keep going through 1? What's going on at 1? Are we seeing all three overlap at 1? No, we got a hole in this one, so we're going to need to exclude that. What about between 1 and 2? We got full overlap of all three between 1 and 2? Yep. What about at 2? All three of them are at 2. Yep, I've got line there, I've got line there, and I've got solid dot there. So all three of them are there. So that's going to be a closed dot. And past 2? No, we don't have the middle one past 2. So that's going to be my final domain. We write domain, we write it out in interval notation, and we're done. Oh, I love that problem. Isn't that cool? Yes.
Number line. But if there's any closed dot, that means that there will not be anything directly next to that. But if we were to continue on front, there was nothing right after.
So I think what you're asking me is if there's a closed dot, that means that on one side or the other, there's not. So technically, this would also be correct. So I can put a closed dot anywhere I want. Closed dot is just indicating that there's a point there that is included, but a line is also indicating that there is a. Does that answer your question? It's messy. I don't like that being there. It's not necessary. It's right. Yeah, question. No, we're going to hang on to that. We'll finish the back page next class. Folks, let me get your